We had actually left, in this particular slide, and showcasing that the total capacitance can be identified using the the driving factor, if the driving factor is mentioned in the gate design, right? Or we can evaluate the driving factor, and then driving factor multiplied by the parasitics multiplied by 3C should give us the overall absolute capacitance, the absolute parasitic capacitance. And the driving factor multiplied by the logical effort should be able to give us the input capacitance. And of course, multiplied by 3C should be able to give us the absolute input capacitance of coming from the next or the subsequent stages. Right. So taking this particular thing forward, let's say that the energy term, okay, so the energy is nothing but the capacitance multiplied by the VDD square. So if I'm considering about the particular gate I, right, so let's say I have a higher order circuit or a large amount of circuit, it's a higher order digital design, and in that particular design there are a lot of gates, and there are a lot of nodes, which is nothing but the output of the gates. And if I pick the ith node or the ith gate, the output of that particular gate I, can be represented, the overall capacitance of that particular gate I can be represented in the form of the driving factor multiplied by the parasitic normalized parasitic factor will give me the parasitic capacitance. And then if it is kind of branched to, if it has multiple branches based on the fan out value, so it could be, fan out of I could be 4, 5 or whatever the number of branches it can have. So based on that, the input capacitance coming from the different branches and then getting accumulated at that particular node I could be stated in the form of the driving factor multiplied by the logical effort. Now, of course, it has to be multiplied by 3C so as to give us the absolute value. Right, so this being the, this particular expression gives us the total capacitance at the output of the gate I. Now with, if I incorporate the wire capacitance also, so the gate I is connected to the gate, I plus 1 with an interconnect or a wire, then I need to accommodate the wire capacitance also. And that is what is accommodated in this second expression. So C wire of the gate I, right? So C wire of I represents the output of the gate I that is being connected to the next gate. And finally, if I want to find out the energy of that particular the gate I or the output node of the gate I, then it will be multiplied by VDD square. So 3C multiplied by VDD square, and then we have this particular expression. This particular expression gives us the parasitic capacitance. This particular expression gives us the input capacitance of the subsequent stage, and then this one will give us the wire capacitance. Now, if I want to find out the energy of the entire circuit, the entire circuit will be nothing but, the summation of I starting from 1 to whatever the number of the gates we have in the circuit. So this particular expression talks only about the energy of the gate I. Here, if I want to find out the energy of the entire circuit with the activity factor at each of the output nodes, at each of the output of the gates, right, that has been there in the entire circuit. So in that case, I need to accommodate the alphas also. And so in that case, it will be 3C VDD square. And then there will be a summation to accommodate all the nodes in the circuit. And within this particular summation, I will have an activity factor. That will be the activity factor of the individual gate outputs. So alpha I, and then multiplied by the entire capacitance we have, right? So the entire capacitance will be nothing but C wire of I divided by 3C plus the parasitics at that particular node I, and then the input capacitance that has been reflected at the node I due to the number of branches we have, right? So in that sense, I will have this particular expression as the energy of the entire circuit accommodating the alpha I. Now, if I can easily modify, I can easily normalize this energy term by taking it out 3C VDD square, right? Because I know that could be that is a constant, so I can actually divide it by 3C VDD square, and then this becomes a normalized energy, and that's what we have in the next slide. So the E normalized, right? So if we identify the E normalized value, then multiplied by 3C VDD square will give me the absolute energy. right? So to have an expression of E normalized, so I will take away the 3C VDD square, and then the remaining expression is nothing but the E normalized expression, which is nothing but the energy of the VDD, energy delivered by the VDD, and that is normalized. Now this particular expression is true for the whole circuit. Whole circuit having the I gates, starting from the all the I covers all the nodes of the circuit, starting from the node number 1 to whatever number of nodes the circuit will have, and inside that each of this will have the parasitic capacitance and then the input capacitance. So in this particular case, what I've taken out is alpha I anyways is is out of this particular expression, and I have also taken out xi value, which is a driving factor of the ith gate. Right, it is the driving factor of the ith gate, and that is being taken out. And so in that sense, I will have C wire of I capacitance divided by 3C and then xi, because xi is taken out. And then here we had xi pi, so we now have, instead of xi pi, we have pi now. And then in the summation we will have xj gj, the logical effort of the jth gate or the jth stage, divided by the xi, right? So this xi will come here because this has been taken it out. It turns out that if I look closely into this particular expression of pi plus the summation of xj gj by xi, this term is actually nothing but the delay term. It's nothing but the delay of that particular ith gate, right? Delay of that particular ith node, right? In fact, it turns out to be the normalized delay for the ith node, right? So remember our linear delay expression, the linear delay expression, right? The linear delay expression says that it is pi plus gi hi. So if I consider the output of any particular gate, so the output of this particular 2-input NAND gate at this particular point, if it is connected to other circuits, other combinational circuits, so at this particular point, what we say is the delay of this particular gate will be nothing but di is nothing but parasitics of this particular gate, which is a 2-input NAND gate, plus the logical effort gi and hi. And if I actually closely watch into this, look into this particular expression, pi plus summation of xj gj by xi, and I have stated this as nothing but the di expression. So somewhere our linear delay expression and then this particular expression, especially this particular expression, should match. All right. Although I have stated the wire capacitance here, right, and I have directly, in the next expression, in this particular expression, I have stated alpha I, xi and di. So although I have stated that di is nothing but pi plus kind of gi hi, so this should resemble the linear delay model. But the question is, where is the C wire I and up divided by 3C into xi going? What it means is this di actually accommodates this wire capacitance also, right, or the delay due to this particular wire capacitance. So that is also accommodated. So the entire thing is actually nothing but di, right? But leaving aside the wire capacitances, the question is whether this pi plus summation xj gj divided by xi, whether it validates to our linear delay model, which is nothing but di is equal to pi plus gi hi, right? So to have a look at it, let's rewrite both the expressions. So one expression says that it is nothing but the pi plus gi hi. Another expression says that it is nothing but pi plus, we have that summation, so gj xj, the driving factor, divided by xi, right? If I have only one branch, I can take out this summation term. If I have multiple branches, this summation term can be should be there. Now let's take a very simple example. Let's say that I have a NAND gate, and I have a NOR gate, so a 2-input NOR. I can have multiple of them, but just for a simple example, let's try to consider this. So if I want to find out the delay for this particular term, so that means this particular output node, right? So the delay for this particular output node will be using this linear delay model, Pi plus Gi Hi will be nothing but 2 plus, this is a 2 input NAND gate, so it will be 4 by 3. And Hi is nothing but the electrical effort or the fan out. So I need to have some kind of an, the input capacitance here, and then the input capacitance of this, right? So in that sense, if I know the input capacitance here, so let me consider some value here, 4 and 5, which gives us the driving factor of 1 in both the cases. So I will have 5 by 4 here. All right, so H value is nothing but 5 by 4. So eventually I will have the delay di in this particular case as nothing but 2 plus 5 by 3. And if I consider the same circuit for our new expression of delay, right? So it will be nothing but for the same output node, let's say this is the X output node. So the delay di from this new expression turns out to be Pi, which is nothing but 2 plus the logical effort not from the ith node. So this is the ith node, and then let's say this is the jth node, not from the ith node, but from the jth node. So it should be 5 by 3. And xj turns out to be nothing but 1 because it is the value, the gate size is 5. So I'll have the driving factor as nothing but 1. And then divided by xi, which is nothing but this particular, the driving factor of the ith stage, which is nothing but 1. So I will now have di as 2 plus 5 by 3. Right? Turns out to be actually be the same. So in this previous expression, so let me go back to the previous expression. What I said was this particular, the energy term now actually is turned out to be a function of the delay di. Right? The energy term, the energy normalized term is now a function of the delay at the ith node. And in this particular circuit, we have, let's say we have a lot of nodes, then we need to estimate the delay at the output of all the nodes and then use that for our energy estimation. Right? So hope this is clear. Now, if I look into this particular expression of Pi plus Gj Xj by Xi, it's a very interesting expression. Now, the question is, inherently the question is, why is this driving factor, this particular expression which we use, the driving factor which we used for the energy expression, is ultimately converted into a delay expression. And the reason is this particular portion of Gj Xj, right? So if I look into this particular portion, so let me use another slide. Yeah, insert the new slide. Okay. So what we were telling is, what we were talking about is the delay expression, which is nothing but the new expression of delay, which is Gj Xj divided by Xi. Right. So if I closely look into this particular expression, and if I want to evaluate this, let's say what is the definition, by substituting the definition of the driving factors, so I will have the logical effort Gj. The definition of Xj is nothing but the input capacitance of the jth node divided by the logical effort of the jth node and then divided by 3c. And Xi, if I want to find out the Xi, the definition of Xi, so this is the definition of Xj. The definition of Xi will be nothing but the input capacitance, right, of the ith gate divided by Gi, this is Gi divided by 3c. So this 3c and 3c will get cancelled. Right, this Gj and then this particular logical effort of the jth node will get cancelled. And what we are remaining is this particular term Gi and the input capacitance. So finally what we have is this particular term actually has Gi and then the ratio of the input capacitance. So the input capacitance of the jth term divided by the input capacitance of the ith gate, right? So it turns out to be nothing but Gi Hi. right? So the delay term is nothing but this particular expression is nothing but di turns out to be nothing but pi plus gi hi. So it turns out to be the same as nothing but the linear delay model. The only thing is, because we are using the driving factor expression, so if we have the driving factor of a gate already available with us, then we can go ahead with this particular delay model. Right? So hope this is clear. Both these delays are the same. Moving ahead, let's take an example here. So let's say that I have an AND gate of the size, the gate size of 4 and the gate size of 5. Right? So let's take an example where I need to find out the delay of this particular node. The driving factor of this particular gate is 1. The driving factor of this particular gate is 1. That's what we had seen. The PI is nothing but the parasitic is 2. The logical effort is 4 by 3. So using the linear delay expression, that is what we had seen earlier, is nothing but 2 plus 4 by 3 into 5 by 3, 2 plus 5 by 3. And here, using the new expression, so this is our, this is our new expression using the driving factor. So pi plus xj gj divided by xi. So it turns out to be nothing but 2 plus, so xj is 1, gj is 5 by 3 divided by xi is 1. So it will be nothing but 5 by 3. So 2 plus 5 by 3 turns out to be the same. Right? So it's the same example which we had seen in the previous slide. Moving ahead, let's take a bigger example. So let's try to evaluate the energy in terms of the activity factor. Right? Let's try to evaluate the energy. So what it means is, if I want to find out the normalized energy term, it will be nothing but the summation of alpha I, xi, and I can do a delay at each of the output nodes. So that is one way of doing it. The other way of doing it is finding out the capacitances at each of these nodes, at each of the output nodes, multiply with that of the activity factor, right? And of course, once you have all those things, all the capacitance, multiply with that of the activity factor, do the summation for all the output nodes, and then multiply with that of the VDD square. So that will give me the average energy delivered by the VDD, right? So let's try to do employ both the methods and try to find out the expressions and try to validate whether both the expressions are same. Right. So in this particular case, let's try to understand this particular circuit at this point of time. So we have the probability, the input probabilities is given as 50%, so 0.5. So all the inputs A, B, C, D are having the probability of 0.5, meaning that the inputs having a logic 1 is having a probability of 50%. And that is being fed to the gates. So the inverters, the input, the inverter output and its probability being 1 turns out to be nothing but 0.5. So I should be able to find out the activity factor, which is nothing but 0.5 multiplied by the complement of P1 will be nothing but 0.5. So it will be 0.25. Let's try to find out the activity factor of this particular gate, the second gate, which is nothing but having a driving factor of x2. Remember that in this particular example, the driving factors are mentioned in the along with the gates. So a value of 1 here represents it's the driving factor of 1. X2 is the driving factor of this 2-input NAND gate. X3 is the driving factor of this 2-input NOR gate. X4 is the driving factor of this 3-input NOR gate, and then so on. The capacitance of 10 and 12 are used. What it really means is it is nothing but the normalized capacitance with respect to the 3C. So the absolute value of these capacitances will be 10 multiplied by 3C or 12 multiplied by 3C, where 1C represents the 1 NMOS, unit NMOS transistor's capacitance. So if I actually want to find out the activity factor of individual nodes, let's try to evaluate the activity factor of this output of the 2-input NAND gate, where the driving factor is x2. So the probability, we need to find out the probability at the output of this 2-input NAND gate. One probability is 0.5 here, the other probability is coming from the input 0.5. Right? So the probability at the output of the 2-input NAND gate is given by 1 minus PAPB. So I will have 1 minus 0.5 multiplied by 0.5, it will be nothing but 0.75. So my activity factor will be 0.75 multiplied by 0.25, which will be 0.1875. NOR gate if I want to find out the activity factor of this, I know what is the probability coming at the input side and the probability coming on the other input. So the probability at the output of the 2-input NOR gate is given by this particular expression. So it turns out to be nothing but PA bar, which is 0.5 multiplied by PA bar, so 0.25, and its activity factor will be nothing but 0.1875. For a 3-input NOR gate, the output expression for a 3-input NOR gate will be very, very similar to the 2-input NOR gate. It will be nothing but PA bar, PB bar, PC bar. And we know the probability of individual inputs here going to the 3-input NOR gate, which is nothing but 0.75, 0.25, and 0.5. Right? So its complement will be 0.25, its complement will be 0.75, its complement will be 0.5. And if I do the multiplication, I should be able to establish P4, which will be 0.09375. And the activity factor at the output of this 3-input NOR gate turns out to be 0.08446. And once I have the probability here, I should be able to find out the probability at the output of this, the inverter, which is also the final output of this particular circuit, turns out to be nothing but the complement of this, because it's an inverter logic. So I will have 0.90625. And its activity factor will be nothing but the same as this one, 0.08496. Now that I have the activity factor, I can actually use any of this energy expressions. So one expression is going ahead with the delay expression. The another one is estimating the capacitances using the driving factors, estimating the overall capacitances at this particular output node by calculating the parasitic capacitances here, the input capacitances coming from the subsequent gates, and then multiplying with the activity factor, doing the summation for all the nodes, and then multiplying with that of the VDD square. Right? So let's do that. The first method we will use is the evaluating the capacitances at each of the nodes, and we have 5 nodes here. So I have written the summation of I is equal to 1 to 5 nodes, estimating the capacitances at each of the nodes, and then we anyways have the activity factor. So we'll multiply that and then do a summation for all the 5 nodes, and then finally multiply by 3C into VDD square. So if I do that, let's start doing that. So the CT1, the total capacitance at the output of the node 1, right, at the output of the node 1, using the driving factor. So I know the driving factor of the first gate, which is an inverter, is 1. The second one, which is a 2-input NAND gate, is x2. The subsequent below that will be the driving factor is x3. So the total capacitance seen at the output of the first node, so which is nothing but the inverter, which is having 1. And then we have the 2-input NAND gate, and somewhere we have the NOR gate, 2-input NOR gate. So what we are trying to identify is the capacitance, the total capacitance here. What should be the total capacitance in this particular node I, which is I'm writing it as node number 1. So CT1. Right, turns out that the driving factor is 1. So the parasitics at the output of this node will be nothing but 1 multiplied by 1. The input capacitance coming from this particular gate and this particular gate will be nothing but plus the 4/3, the logical effort of this 2-input NAND gate, multiplied by the driving factor, which is x2, and the driving factor here is x3. So I will have the logical effort of 5/3 and then multiplied by x3. So that is what we have. So I have this particular expression giving us the capacitance at the output of the first gate. Multiplied by 0.25 is our activity factor alpha 1. So similarly, I can actually estimate the overall capacitance and then multiply with the activity factor. So for alpha 2 C2, the total capacitance seen at the node 2, which is nothing but this one, which goes to the 3-input NOR gate with x4, right? So in this sense, the parasitics at this particular point, so this I'm going to write it as CT, total capacitance at the second node, which will be nothing but the parasitics coming from this particular gate. So the parasitics here will be nothing but x2 multiplied by 2. So I have 2x2 here, and then the input capacitance coming from this 3-input NOR gate will be, the logical effort is 7/3 multiplied by x4. So that is 7/3 and x4. So I'll get this particular total capacitance multiplied by 0.1875. Right, so this is what I have it for both x3 and x2. So I have 2x3 plus 7 by 3 and x4 multiplied by 0.1875. CT4, which is the total capacitance at the output of this 3-input NOR gate. Remember that this goes to the inverter as well as it has a physical capacitance of 10 capacitance, right? So a normalized 10 capacitance is there. So I will have the 10 and its own 3-input NOR gate. Parasitics is 3 and a driving factor of x4. So the parasitic capacitance is 3 into x4 plus the input capacitance coming from the next stage, which is an inverter, having a driving factor of x5 with its logical effort as 1. So I will have input capacitance of 1 multiplied by x5 plus the additional load capacitance of 10 is there, multiplied by the activity factor here. The last one, which has only the parasitics, 1 into x5 plus the load capacitance of 12 is there, the normalized load capacitance of 12 multiplied by the activity factor. So now I have estimated all the alphas, alpha into capacitance. That means I have estimated the activity factor, the product of the activity factor, and then the total capacitance seen at the individual nodes. We can add it together up and then multiply by 3C into VDD square should be able to give me the energy delivered by the VDD, and it's an average energy delivered by the VDD per clock cycle, right? So if I use a different method, if I use a delay method, remember that we had evaluated the energy expression in terms of energy expression as a function of delay. So if I use that, all right, if I find out the delay at each of the output nodes, right, and then use that in our alpha I xi di expression for 5 nodes, right, whether my expression calculated, the energy expression calculated from this particular method will resemble to the one which we had calculated in the previous slide. Right. So for doing that, I need to find out the delay at each of the nodes. So D1, D2, D3, D4. And the delay expression says that it is nothing but Pi plus, the summation of Gj, Xj by Xi. So it is nothing but the logical effort of the next stage multiplied by the driving factor of the next stage divided by the driving factor of the previous stage. All right. And we can also actually calculate the delay using the linear delay model with Pi plus Gi Hi, and then that also can be accommodated into our energy expression. So in this particular case, I have taken this particular expression because we have anyways derived it, right? So it will also become a good example for us or a good exercise for us to solve this using this new expression, because we are anyways adapted or used to this particular expression. So why not use this particular expression and see that and then apply that for our energy expression. Right, so one could actually use this expression also. So if I use this particular delay expression, so D1 will be nothing but the inverter. The first gate is an inverter, so the parasitic of 1. And then we have the Gj and Xj of the subsequent stages, wherever it is kind of branch. And remember that the output of the inverter is kind of branched to, the 2 gates. One is a 2-input NAND gate and another one is a 2-input NOR gate. So I will have 4 by 3 in X2 and then 5 by 3 into X3. Coming from this numerator term divided by Xi, which is nothing but 1. D2, the delay of the output of the 2-input NAND gate, which is nothing but parasitics of 2 is there, plus Gj, Xj. So it is going to, the subsequent stage is a 3-input NOR gate. So I will have 7 by 3 as the logical effort multiplied by X4 divided by X2 is there. Right, so that's what I have written here. Similarly, D3, I will have a similar expression, 2 plus parasitics of the 2-input NOR gate is 2 plus the subsequent stage, the logical effort is 7 by 3 here. This should be 7 by 3 multiplied by X4 divided by X3. Delay of the 3-input NOR gate output, right? So the 3-input NOR gate and its output, and then I want to find out the delay at the output of the 3-input NOR gate is nothing but the parasitics of 3 plus, it is fed to the next stage, which is an inverter. So I will have the logical effort of 1 and then X5, the driving factor, plus it sees a load capacitance here, a normalized load capacitance of 10, and then that gets divided by X4, right? And finally, I will have, the parasitics, the output of the last stage, which is again an inverter. It sees a parasitics of 1 and then we will have the load is nothing but, it doesn't have a logical effort because the output is not connected to any other gate. It is actually connected to the normalized capacitance of 12. So it uses the 12 capacitance divided by 12 normalized capacitance divided by the xi value, the driving factor of the fifth gate, which is nothing but x5. So if I use this particular delay expression and put it into an energy expression, then I'm likely to get this particular expression. Turns out that both the expression, the one which we calculated earlier in the previous slide and this particular expression, turns out to be the same.